Welcome to this lecture. The lecture is called Aerosol and Nanotechnology, and I shortly introduce myself. My name is Samir Salame. I'm since 2 years a professor for particle technology and a little bit recycling economy. But my main focus is particle technology. So I studied industrial engineering and management, so half economics, half engineering, and then I very fast went into engineering, and at the time as a student I saw a poster about particle technology and I thought that's the most boring thing you could do in your life. And then a few years later I decided to make a PhD in this topic. And it was quite interesting because it was not the topic, but it was the professor at this time, because I want to work with him. I didn't care about the topic so much. I had the feeling he could teach me a lot. And then I discovered the field, and then I figured out that's a very, very interesting field. And basically this is how I ended up in particle technology. Then I made a postdoc. This is something you do after, basically when you're first time an independent researcher, so you have your PhD, you're able to do research on your own. And then I did a postdoc in the Netherlands. And then I went to industry. It's a big company, a French company called Saint-Gobain. And there I worked on glass. It's a completely different field, which I would like to experience. And I learned a lot during this time, working in a completely different field. So also something I really couldn't suggest to you, sometimes to change fields to get some insight into other things. And then quite fastly, I tried to go back to university and prepared this quite a lot. And then since 2 years, or now it's the 3rd year, I'm here in Münster and working on particle technology. And so far the lectures are growing, and also I'm starting to build up a research group, and we are also quite on a good track with this. So if you have any questions to this, please let me know, and we can always discuss about that. The first thing, before I ask you some questions, is that you should know this lecture is scheduled in the way that we have 2 hours of lecture and 2 hours of seminar, okay? So whom of you heard particle technology with me? You, right? You're the only one, probably, you, but you don't take the class anymore. Exactly, so in particle technology, it's by the curriculum similar, but there we have 4 hours of lecture. And here we have 2 hours of lecture, so today we are done after 90 minutes, okay? And we have 2 hours of seminar. But you have to prepare things for the seminar, okay? Because aerosol technology and nanotechnology is strongly related to science. While particle technology, the other class, I try to put it or move it more, at least more. I'm not completely there yet, as you know, but I try to move it more towards industrial application and industrial cases, and here it's a more research-oriented class. So this is why we need the seminar. Okay? And in the seminar, we will discuss papers and other things, and you have to prepare, therefore. I take care that the amount of time is not too much, but if nobody is prepared, we are done, okay? So if everybody comes unprepared into the seminar, there is no seminar, okay? It's quite easy. Any questions to this? Good. Then I would like to ask you about what do you know about aerosol, nanotechnology? What are your expectations for the class? What do you hope to learn, think you learn, want to learn, or whatever? Who has any ideas or any expectations from the class? Yeah?
I don't know too much about nanotechnology.
Already marked some quite important points, and this is sprays. We will learn a lot about sprays. We will talk a lot about sprays. Pharma industry, very, very important. And probably inhaling was also something we will talk about this too. Okay, very good. Any other ideas or whatever? Or why do you take this class? Yeah? Exactly, so nanotechnology is getting more and more important, and already today we will learn a little bit about this. I hope we will learn a little bit about this. What else? Very good. Yeah, that's very good motivation. So you think it's something you want to learn. It's an important topic. And you also mentioned nanoparticles. And that's exactly, if you look, particle technology. So for sure, we will have this crossing of nanoparticles, aerosols, and nanotechnology. And I want you to understand this relation. So what's about you? Okay. Okay. That's a very good answer. I hope to hear it because it's a very common answer that people somehow heard about nanotechnology or know something about nanotechnology, but not so much about aerosol technology. Aerosol is something, as a chemical engineer, you don't get so much into touch with it. At least, I guess so. Maybe if you go towards pharma, that's one thing. Okay, yeah, very, very good point. And what's with you? Mm-hmm. Okay. Okay, but you mentioned something also very important we didn't have before, and we will touch this probably already today, and that you said about nanofibers. Okay, so we talked about particles, and particles normally is related to spherical particles, but of course they could have a lot of different shapes, and these shapes are extremely important. Okay, and we want to learn something about this, and fibers are there very, very important. We will have also a lecture related to this. So thanks for your inputs. And what I always want to show you is this slide at the beginning of the lecture. So I will give you a promising empowerment, and this promising empowerment is 4 points. And these 4 points will be the whole semester the same, to just always invite you to the lecture and to remind you what we are talking about, because we only see us on Monday. So in this class, you will get a good overview about aerosol technology at all, okay? So I will try to introduce this topic, aerosol technology, to you. And as you mentioned, most of you don't really know what aerosol technology is, okay? And today, and this will be then always new, is these smaller points below is what we do today. So these 4 will be always the same. And today, I just will give you a first insight into aerosol technology. And of course, we have to discuss what is an aerosol. Okay, after today, you should know what is an aerosol and have some ideas how it is connected to some other things. Okay. Then you should know how aerosols are moving. Okay. And you see, it seems to be a very, very important point because I have it as 1 out of 4 points on the slide. So the movement of aerosol is very critical, okay? And we will touch this very often, a lot, not today, okay? Today is introduction, but the movement of aerosol is a key knowledge I want you to take out of this class. Then I want to give you the idea about technical applications, because it's in the name, aerosol technology, but I guess most of you don't really relate aerosols to technical application, to a field of engineering, okay? You are engineers, and we have an engineering class, so there should be a correlation of aerosol and technical application, and today we will look at one first small example, and this is carbon black. And the last one is related to nanotechnology, because I want to understand, or that you understand this correlation or this connection, not correlation, connection from nanotechnology to aerosol technology. Where are they the same? Where are they different? And why we have the class called aerosol and nanotechnology. And today we will have just a very short intro into nanotechnology as well as aerosols. Any questions to this? Then we have to make some organizational stuff, and one of these organizational stuff is how this lecture works. The lecture works in the way we have lecture here, okay, 90 minutes. Probably we make 5-minute break in between because 90 minutes is quite a long distance. We have the seminar, and you have to make 2 homeworks, okay? And these homeworks are mandatory. In particle technology, it's about 4 homeworks. Here we have 2 homeworks, okay? And these 2 homeworks, each of them counts 10% to your overall grade in this lecture, okay? And you have 1 week time to work on it, and then you have to upload it on Ilias. There is an Ilias folder, I opened it today, so we will use Ilias for the slides. Normally you will get the slides before the lecture. The slides I give to you are always a little bit different than the ones I used here, because I use a lot of pictures you don't know. I use a lot of storytelling, which you don't need to know during the lecture, but the slides normally will be uploaded before. So the thing is, very important, each student has to upload his own solution, okay? So you can work as a group, and if I would be you, I would work as a group. I would never work alone on these homeworks, okay? The idea is to do it together, but you cannot upload a group homework. And I will not react to emails in this case. So if you try to send me your homework, you can try whatever you want, but to these kind of emails, you will not even get an answer from me, okay? Because it's unfair. If you have questions about the homework, you can always ask me. And if you have questions, you will always get an answer. But if you try to play around with these deadlines and these things, no chance. The most fair is Ilias. You just have to upload your own solution, okay? Important here is these are not bonus points. These are fixed points, okay? 20% of the grade is the homework, because I want you to work during the semester. I don't want to make everything at the end of the semester, the full pressure at the end of the semester. I want you actively working on this. And then is a second one, since this is a class very related to science, your job is to group in a group of 2. So I give you 2-3 weeks time for it, then I put a list here and you have to make group of 2 persons and you just sign in. If you don't find somebody, just let me know. I will help you with this. I don't want to figure this out at the end of the lecture, 1 week before the exam, okay? Do this during the semester. And in this group, you have to work on 1 paper. And I want you to write a summary of 1 paper, scientific paper, okay? And this summary should be around 3 to 5 pages. Now probably you ask, okay, what count as a page and whatever. 3 to 5 pages, and I don't really discuss if a title is part of a page or literature is part of a page. So if you have 1 written page, 1 page title and 1 page literature, it's technically 3 pages. But you can imagine about the ranking. If you have 5 pages plus 5 pages of literature and so on, it's technically 3 till 5, but I don't discuss this, okay? So try to make a meaningful summary of 3 to 5 pages, and if you have a 6th page, which is a title or whatever, that's fine, okay? Why 1 paper? Because I want you to understand that writing a summary is something different than writing a review or writing about generally a topic. There are all kinds of papers and kind of writing, and here we choose to make a summary because I think none of you has so far written a summary of 1 paper on this scope. Or does anybody has done this before? And the summary of 1 paper, you will see, it's not that easy because you just work on this 1 paper, okay? So, and you also have to present. And presenting is a little bit different because the presentation should be around 10 minutes. Could be a little bit less, but it should be around 10 minutes. And you are not allowed to use PowerPoint. So you have to think a little bit more creatively of your presentation. And that you're not allowed to use PowerPoint really means don't use PowerPoint, don't use LibreOffice. It's technically not PowerPoint, but this is not what I mean here. And what you should also not do, even if it's technically work, you could just show pictures or a PDF of a PowerPoint. Don't do this, okay? This is ranked. And part of the ranking will be if what you show is basically the same as a PowerPoint presentation or if you have a different way. What is, for example, a different way is a poster presentation, okay? This is something really different than a PowerPoint presentation. showing pictures with text and just click, 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 even if it's pictures, is basically the same as a PowerPoint presentation. Doesn't mean that you're not allowed to show pictures, but do it in a different way, just like this. And this part counts 20% of the grade. Any questions to this? Okay. And this means at the end we will have something like an exam, and this will be an oral exam. So in the past people could choose, because I don't have a fixed person who takes the exam with me. Now I have a PhD student, so all of you can make an oral exam. And I'm not a big fan of written exams in the master, because written exam, all of you know how to write an exam, and written exam is very far away from what you do in industry. You don't write exams in industry. But what is much more closer is a pressure situation where you have to talk to somebody, where you have to defend yourself and all these things. And this is why I want to have oral exams. And there is only one oral exam per semester. I know that in other classes you have 2 per semester, but I'm also not a big fan of this. The advantage of the oral exam is that we are very flexible with the appointment, okay? But I don't want to have these repetitively, I try it and let's see, and then 2 weeks I come again and try it again, and then we see, and next semester I can try it twice again. I don't like this so much, okay? So 1 exam per semester, you well prepare, then there's no problem. If you're not well prepared, it doesn't make sense to repeat it 2 weeks later, okay? But even if we have a fixed one in the schedule, we can find different appointments for you. That's the big advantage. So we can shift the appointment as it fits to your schedule, but once per semester is, in my opinion, the best we could do. And this one counts only 60%, okay? And this means it takes pressure from the exam, okay? Because already before you already have 40% of the grade in this class. So now you could calculate and figure out that there is a possibility to fail the exam but pass the class. No, it's not. You have to pass the exam, okay? Anyway. So without passing the exam, you don't get this module, okay? And I really suggest don't start all these calculations, how many percent to what and what should I do to get which grade. Just do your homeworks, do the seminar, do the exam, and the rest. And all the energy you could put in all these kind of calculations, put them in the homework, put them in the lab class, put them in the exam, and then you will not have any problems to pass this class. Okay? Any questions? I will upload the slides, of course. And then another thing is, as you probably already see, I want to record the lecture. In the past, we streamed the lecture live, and now I want to record it, but we have to see if it works or not. At the moment, I see I have some problems with the camera, so we have to check. It works quite well, but I have to adapt it, and then I have to figure out. So this means I cannot ensure that all the videos will be available. It's something we try, but it's not something you can rely on, okay? And if the class is empty, I don't give a class, okay? And then there is no video. So if you think, oh, nice, all the classes will be on video, I don't come, nobody comes, no lecture, that's it. And we don't know how long the proceeding takes care. So I don't know if I will upload them this semester, okay? There is nothing you can rely on the videos. It's something I want to do. It's something I would like to have for you as an additional help for learning, but I cannot make you any promises at this point because we don't know how much time it takes, how much does it work, and all these things, okay? So please don't rely that we have every week a perfect video uploaded of the lecture. We still don't know. I will try to adapt the lecture a little bit. So normally I run much more, and now I cannot run so much because of the camera to this. And this is also why I have to repeat when you ask questions, because it's not, nobody will hear your voice here, okay? But it doesn't mean that you should not participate, because nobody knows whom is giving the answer. So you don't have to be afraid. And in my lectures, you have to participate a lot. And if I see that this interferes with the recording has a lower importance, okay? The most important is what happens in the class, okay? So there's no reason to be afraid, because I anyway have to repeat what you are saying, and nobody sees you, so don't be afraid about this. And if everything works well, we will have lectures, video lectures, and you can use them for the homeworks, you can use them for the preparation of the exam, but without any promises. Questions? Yeah? Mm-hmm. Yeah, that's a very good question. So we always have the seminar, and in the seminar we will have fixed appointments for your presentations, okay? So in the seminar, but we will discuss this next week in the seminar. In the seminar, I will rank or mark 3 appointments during the semester, that you can do it quite early in the semester, that you can do it in the middle of the semester, or that you can do it at the end of the semester. But I ask you to don't ask for extra appointments, okay? It's not, or I cannot organize the seminar if everybody has a different idea. And also, something I really ask you, if you have ideas or problems or whatever, send me an email, and please do this on a fair time, okay? So if I get on the last lecture emails like, I have to present, we have a full semester to plan this, okay? And we will make the planning in the semester, but please don't bring me in the situation where everybody comes 2 weeks before the oral exam. I have to do this, and here I have to, can we make an extra appointment, okay? No. You will have 3 appointments chance to do it, and if you don't take these 3 appointments, next year is another class, okay? Other questions? Okay. Then is one thing which is very important for me, and this is the literature, and I also have the books, or some of the books here, and basically the lecture is a copy of this book. And this is a really amazing book, and it's also in the library, so you can, I ordered a few of them, please share it with the others, right? So don't take it and hide it somewhere, because I don't have 20 versions of it, but we have a few. And the lecture is very strongly oriented on this book, because this is an amazing book, okay? So that's the first thing. Then there is a book from Sheldon Friedlander, Smoke, Dust, and Haze, which is content-wise extremely good, and it's kind of the Bible of aerosol technology. But for students, it's not so easy to read, okay? It has a quite high level, and it's also, in my opinion, not so easy to follow if you're not already have a certain level of knowledge. And this means it's more like a backup book. So, but I would refer the Aerosol technology book. The good thing is there is a new version since Corona. They made a new version, but they don't change anything. So you can use the old book. And so if you use the old book, you will not fail anything. And then there are other books, as you see here, and one is these Engines of Creations, and this is this book. And this is a book related to nanotechnology. It's an amazing book from a guy from MIT who in the 80s has some nice ideas, or 89, about nanotechnology. And this is a really good popular science book, okay? So it doesn't have equations or whatever like this book, but there's a lot of technical stuff, a lot of ideas about nanotechnology. So if you want learn a little bit more, I recommend this book. And I also, and then I have to go back also to the other slide, there is a book called Prey from Michael Crichton. Whom of you know Michael Crichton? All of you have seen a movie from him, I bet. Who knows Jurassic Park? Okay, Jurassic Park is from Michael Crichton. Who knows Emergency Room with George Clooney? It's from Michael Crichton, okay? And Prey is also from Michael Crichton, and this is about nanotechnology, and this is a really good science fiction book, because what he's doing, he is really making science fiction, okay? So he takes science, makes a story out of it, makes a little bit bigger story out of it, But at the end, you can really learn a lot about nanotechnology in this book. And this is also one of the reasons why here you can also choose a science fiction book for your summary, okay? But if you choose a science fiction book, I want you to work out the technical idea and application of this book, right? So in Prey, for example, is a very, very strong description of technology, okay? So if you choose to make a science fiction book, you're very welcome, but then you really have to look into the technology. And there's another one, which is also one of the first nanotechnology books. And this is Diamond Age. It's also amazing. So there's a lot of things nowadays we have, which were nicely described. The technology is very nicely described. And there are a lot of good books. I even don't know all of them, but these books are very helpful in the class here, okay? So if you know any of these books, just let me know. If you know movies, let me know. And since we are thinking about recording it, then you also could put it into the comments of the video. If we load it up, then we push the video a little bit. Because I don't know good movies, I know a few good books. So if you know them, just let me know, okay? Outline. So this is also something I will show you every lecture, or just to recap a little bit. And what you see here is, okay, today is quite simple. It's introduction. Next week, we will talk about aerosol characterization. And then you see 3 lectures about aerosol transport. So you see the movement of aerosols seems to be very important because we have 3 lectures about the movement of aerosols here. And then you get, and this is what you see here, your first homework. So here will be the first homework, which you have to do. You have 1 week time. And then we talk about some other stuff, and this is light scattering, experimental methods, coagulation. I don't know if anybody of you knows what is coagulation. Yeah? What is coagulation?
It's like when we bleed,
Mm-hmm.
there is some particle formation inside it,
Mm-hmm.
which inhibits the bleeding of it.
Mm-hmm.
So there are 2 ways. I don't remember that much.
Mm-hmm.
So it was in my second semester, third semester.
Okay. Yeah, we will see. I mean, I agree. It's related to bleeding, but it's a more general term. Okay. And I really would like to, at least it seems to be important. We have 2 lectures about it. So I hope you see, and then we will see how is the relation to bleeding. Okay. Then the second homework, and then we have some other classes, gas to particle conversion, carbon nanoparticles. So there's really a full class about carbon nanoparticles. The shape will be fibers, right, will be important again. Adhesion at the nanoscale, one of my favorite topics. And at the end, I will talk a little bit about nanorobots, because then the lecture is nearly done. And we will also repeat a little bit in this lecture. But importantly is that for the exam, of course, all lectures are important, not only the one with homeworks, okay? So keep this in mind. And keep also in mind that we have a larger break here because of Easter, right? And I'm also a week away, so there's a small gap of 2 weeks where there's no lecture, okay? So we have 2 lectures, then you have a short break, and then we go through the full semesters. Any questions to the outline? Okay, then I would like to start with nanotechnology a little bit. And with nanotechnology, we have to start with one of my favorite guys. Who is this? You can read it from the slide already. Okay, who? Okay, that's another thing, but it's Feynman. That's correct. Yeah?
I think you are the first guy to talk about nanotechnology, about modifying nanoscale level.
Exactly. So he does not use the term nanotechnology, but he was talking about, and this is the lecture he gave. Okay, the lecture he gave was at the meeting of the American Physical Society. I have to read it, 1959 at the Caltech. And there's always like a keynote lecture of a big physicist, and he won the Nobel Prize. I don't know in which year, but he won the Nobel Prize, so he was a big guy. And in this lecture, he basically gave these plenty of room at the bottom, and then he said, okay, what I want to talk about is the problem of manipulating and controlling things on the small scale, okay? So the small scale, and this is what plenty of room at the bottom, so down there at the bottom means at the small scale. And it was quite interesting because he said, okay, what I'm talking here is not much about fundamental physics, okay? We will not learn many things about how the world looks like or whatever, but what I'm talking about has a lot of technical applications. It's a physics of technical applications, and that should be very interesting for us as engineers, right? Because we're thinking in terms of technical applications. And then he said, okay, but if we make things so small, we could write and read small. Okay, this is something we could do. And you have to imagine at this time, 59, this was a big thing. Because they don't had computers, they don't had mobile phones, they don't had PDF, okay? So what they had is books, which you have to send around. And books, they had at this time 24 million big books, which they really need. And you have to deal with it. They are super expensive, they are big, you need a big library and so on. He said, basically, we don't need this. We could write very, very small, and physics doesn't say anything against it. So what we can do is, we can create letters which have a diameter of 1,000 atoms. Okay? And if we do this, we can write the full Encyclopedia Britannica. This was the book he's always referring to. We could write this on the head of a pin. So very, very small. Okay? And then he said, okay, we can also read at this small scale. And if we read at this small scale, we need better electron microscopes. Okay, they had electron microscopes at this time, but they were quite limited. And he says, the physics we have says nothing against better electron microscopes. And if we have them, we could answer some very, very important questions in biology. For example, at this time, a very important question was the structure of RNA. Today we know it, at this time they didn't know it. And he said, in chemistry, we really would need better electron microscope because the analysis we have is not so good and we not really know what happens in a lot of cases, and it's better if we can look at what is happening, okay? And this is what we can do nowadays with electron microscopes. And he even said, okay, 1,000 atoms is even still quite large. So if we use different methods for a letter, we can create a new code with dashes and dots. And then we just need 100 atoms for a dash or a dot. And in this case, we could write all the knowledge of all books on something like 3 times 3 millimeter. Okay, that's all what you need, and there's all the wisdom of all books. And everybody could read it with these kind of electron microscopes. And then, because he was a big fan of biology, he also says about, yeah, but what is the difference from biology to this? And he says that biology is not only storing information at the small scale, if you think about DNA, right? But biology is also doing something with it. So it's processing it. And we should be able to do the same because the law of physics doesn't say anything against it. So basically we should not only read small, but we should aim to do the same as biology. And on this very, very small scale, we should process things, we should create things, we should be active on this size level, okay? And one example he had is the miniaturization of the computer. At this time, the computers were very, very big machines. And these big machines could calculate, and that's it. And he said, okay, but there's nothing, and that's quite remarkable. He said there's no reason why the wires and transistors of a computer should be in the size of 10 to 100 atoms. Do you know the size of transistors nowadays, roughly? Any idea, the transistors, the diameter? 1 meter, 1 millimeter, 1 micrometer?
The micrometer, I think, in the chip, they just say that it is 5 to 10 atoms.
Yeah. So we are exactly more or less in the size range he's telling, 10 to 100 atoms. Like, and he said, okay, if we are in this range, we can have so many transistors in a computer that the computer not only can calculate, but the computer can make a judgment which method of calculation is the best. And this is what we're doing at the moment, right? With AI and so on, we try to bring the computer to make judgments. And he was able to relate the computational power to these diameters. At least he had an idea about it. Don't know how much he really knows it. And he gave a very interesting example. I don't know if you read in the news, but there was an old terrorist which was identified now from a Rote Armee-Fraktion from the 70s, 80s here in Germany. Does anybody know how they figured out that because she lived 30 years in the underground, and now they found her? It was basically, as far as I know the story, it was a Canadian journalist. It has to do a lot of identifying pictures, okay, face recognition. And Feynman was telling this, if the computers have these transistor sizes, they are able to make face recognition. Because in this time, a computer can only recognize a face if the pictures are completely the same. But if you show a different emotion, the computer cannot recognize. But he says if the computer would have this power, he could do this kind of face recognition like the brain can do it, right? I would, even if I have a picture of you where you look angry and then I see you smiling, I would recognize you. And in this time, the computer couldn't do it. And he says if the transistors go down from 10 to 100 atoms in diameter, the computers are able to do it. So he made a lot of very good predictions. And what I like is that he's not completely going anarchy with his ideas, but he tried to make very distinguished points. And the last thing, what I really like in his talk, is that he not only tells what we can do, but he also says how we can do it, okay? And that's another important thing. Of course, you can have any kind of crazy ideas, but the question would always be how you can do it. And he quite detailed write down how things could do. For example, he talks about chemical vapor deposition. Whom of you have known about chemical vapor deposition? Yeah. Did anybody of you already worked with chemical vapor deposition? Yeah. In lab class or which lab class? Okay. What do you grow there with chemical vapor deposition?
We made layers for LED.
Mm-hmm. Yeah, exactly. And he really has these ideas to use these kind of techniques. And also he described much, much more. You just can download the paper. It's 10 pages or so, and it's a talk. It's not a scientific paper. And I really, really recommend what he was telling there together. He's also talking about nanorobots and these things, but I just choose 4 examples about it. And another thing is, because he write and read small, which is a really, really cool example. It was taken 2007 by Professor, or by Uri Sivan. He's now the president of the Technion, and some other guys, but him I know because I worked with him. And he took this, and they had kind of an educational project, and they said, okay, we have to interest young people in nanotechnology, and it's also about, I don't know, whom of you can imagine 1 nanometer? I cannot too. And the normal comparison is that you say, okay, you take the Earth, that's 1 meter, and then you take a football, that's 1 nanometer. But I cannot imagine the Earth, so that doesn't really help me. And what they took is, they took a book, in this case they took the Bible, right? And they said, okay, we can imagine this, and we have 6 millimeters roughly of letter size, and it's 1.2 million letters, at least in the Old Testament. I didn't count them, but I found this information. And then they said, okay, we just make 1 page, not a few hundred pages, and we reduce the size of the letter from 6 millimeter to 60 nanometer, okay? And this is one of the Bibles. You can buy them now for 20 euros or $20, you can buy them. And here you have on 1 page the whole Old Testament. The original one was sent to space 1 or 2 years ago. This is the original one. The original one is even smaller, okay? But this was done with focused ion beam, and this is done with CVD, I think. So it's easier. So you have 1 wafer, and then you can make 20, 30 out of them. And I will just give it to you. And this helps me much more to think about which size scale we are talking about, okay? So here are 1.2 million letters with 60 nanometers. So always, if we talk about 10, 20, 50, 100 nanometers, think about these nanobible, okay? So this is a very cool example of very creative science of nanotechnology, but it's of course not only about benefits. What is another thing next to benefits related to nanotechnology, very often also in the news? What do you think? Air pollution, okay, what is air pollution? Not in detail, I want to have more an umbrella term.
Like its negative part?
Yeah, exactly. So the risks, right? So we have the benefits and we have the risks, and there's a very interesting study about it. And the study which is what you see here. And the study is from 2004. So you always have to imagine, it's a survey, they ask 1,500 US Americans, but you have to imagine it's 2004 and not 2020, okay? So 2004, we didn't had these things really much, right? So we didn't had Facebook, or all these things were starting. So imagine it was still a different world. And if you find a nice or a newer study about risks and benefits about nanotechnology, please send it to me, okay? So it's a voluntary homework, because nowadays probably the results would be a little bit different, and this is something you always keep in mind, okay? So one thing is the result of the study, and the other thing is when was it done? And here you see that about 1,500 people were asked, did you heard nothing, a little, or heard some about nanotechnology? And you see that most of the people have heard some or heard a lot, only a few part of the people have heard some or a lot about nanotechnology. I would like to see how these numbers are changed till today. It should change somehow, but I don't, from here to here probably, but I don't know if from here to here the numbers really changed, okay? And what is very interesting in the lecture, in the study, is this graph here. So the people should judge if they think nanotechnology has more benefits or nanotechnology has more risks. What is the outcome of this slide? What do you see on this slide? Exactly, very good. So, and that's an important message. So there's also another message, and this is that I don't find an emoji which represents low knowledge without getting problems. That's the one thing. The high knowledge is quite easy. You just take an academics and that's it. For low knowledge, I don't have any idea. But exactly as you say, so the judgment, if you think there are more benefit or more risks, is related to knowledge. And this is what we see extremely during Corona, okay? During Corona, you really see the people who don't have any idea about medicine read 2 or 3 articles and now think they can judge that the risks are much, much higher. Okay? And you see the people who know about the topics, they judge different, okay? And this is significantly different. And this is because you're not able to judge the risks. You're afraid of the risks. If you don't understand chemistry, it's really hard to judge a chemistry, a lab, right? If you don't know anything about chemistry and you go into a lab, you would not touch anything. And you see just these marks on the bottles and probably, but if you trained like you for 3-4 years, you can move very easily through a lab, right? You know what to touch, what not to touch, how to touch things, when to wear glasses, when to wear gloves. When do you wear glasses in a chemistry lab? Always, exactly, very simple. And this is something which not only counts for nanotechnology, okay? So it's a very important takeaway message, and this is why it's important to always consider the knowledge of persons when they judge something in terms of risks and benefits. What do you think is the area of technology or market, if you think in terms of products, which benefits the most from nanotechnology? So if you're a company or a consumer, which field would probably benefit the most from nanotechnology? Medical, very good. Why? Very good. So there are a lot of applications in medicine. I mean, now we are a little bit biased. Probably if you make a survey after Corona and before Corona, the amount of people judging for medicine would be different because of the vaccinations. What else? So we have, sorry? Electronics, okay. What kind of electronics? Okay, so IT, yeah. Okay, what else? Food, very good. Actually, you also see it in Fanta. The orange size is nanocarotene, okay. And also there you add some nanoparticles. What else? So we had food, we had IT, we had medicine. What else? Sorry? Perfumes, okay. Perfumes are interesting because of the atomizer, right? Because of the small droplets we are creating, okay. But then it's more about molecules, right? Okay, so yeah, I agree. But it's also always important, and this will be also part of the lecture, to distinguish between molecular chemistry, aerosol, and nanotechnology. But we have a lot of overlaps. We will see this next week in the lecture, okay? Yeah? Cool, coatings and all kinds of products. So coatings is more the technology, but it's related to all kinds of products, okay? Yeah, exactly. Cosmetics, sunscreen, and a lot of other examples we have, but cosmetics exactly is one. Material strength or material development in general, okay, very good. So in the survey, they distinguish it in this way, that they say cheaper and better consumer products, new ways to detect and treat human diseases, and there you see that's medicine, and 60% think, okay, nanotechnology is related to medicine. And from research point of view, it makes also sense because here you get a lot of money for research. There's a lot of money in there. Increased national security and defense. New ways to clean the environment, which could be interesting because 2004, it was not that big topic, right? It was not as prominent as today. And what is very interesting is physical and mental improvements for humans. And there were also 12% who think about this. Okay, what is about, these are benefits, and you see how they are judged, the benefits. So there's a clear towards medicine. What's about the risks of nanotechnology? Where are the risks? Exactly, so inhale, nanoparticles, nanofibers, extremely dangerous, right? Nanoparticles, not always, but we will talk about this. What else? What could else be a risk? Yeah? Yeah, nanoplastic, exactly. While nanoplastic often is also in the micron range, microplastic, right? But nanoplastic also, maybe we will cover this at one point in the class, if it's really nano or microplastic or the size ranges there, okay. What else? What kind of risks? Particles that can accumulate in the body. Any example? You know any example for this? Yeah, so nanoplastics you will find in our lungs nowadays because from tires it comes and all of us will have some nanoplastic in the lungs. It is as it is. What else? Smoking, exactly. And smoking, and this is here my brother-in-law, he smokes. Is anybody smoking here? Yeah? Yeah, don't be, that's fine. I don't smoke, I smoked in the past. Nowadays, less people smoking, at least in Germany. But scientifically, smoking is extremely interesting. So we could make the whole class on this slide, okay? And we will always see the slide again and again and again, and you will always discover something new on this slide. But here you just see an aerosol so far, okay? So the question is, what is an aerosol? And at least I want to bring something on the board. And this is that an aerosol is a heterogeneous mixture, heterogeneous, is correct? Yeah. Mixture of particles together with gas. Okay? So, an aerosol is a heterogeneous mixture of particles together with gas. And this is what you see there. But you can say something of the type of particles directly from this slide. What? It's important for the terms particles here and related to an aerosol. The size is one very important thing, exactly. What is probably the size of aerosol particles? They are spherical, at least here in the image. We will learn if they are really spherical, but it's a good point, yes. Some are, some not, and we will see why. But what do you see in the middle part? And probably something with exactly. So normally you would think in terms of particles or, about a solid, okay? But in the terms of aerosol particles, and you have to take care in the literature, because for me also particles are generally solid, but aerosol particles mean droplets and solid particles. So droplets like water droplets, and solid particles could be smoke, could be minerals, and all these kind of particles. And this mixture is an aerosol, and they are surrounded by a gas. And for this class, we will not always have this clear definition, because we learn a lot of things which are also working in liquids. Okay, we very often have examples of nanoparticles in liquids, but we use aerosol technology. So the definition means we have a heterogeneous mixture in gas, but the knowledge and the theory can be used for things also in liquids or in other gases than air. So, the aerosol particles, you said something about size. And size means that the particles are stable in air. And when we talk about the movement of particles, we will figure out what this means, stability. And stability means that they not directly fall down. So for a few hours, they stay in the air. Okay? So they are, at least this one we could say, they are stable for at least a few, oh no, I cannot write a few hours in air. One number you should really keep in mind is the low. Do you think we have aerosol particles here in the air now? Yeah? How many? Yeah, but how many? What do you think? Make a guess. 1, 2, 3. Billions? Trillions? 1 cube centimeter, 1 cube meter, or in this room?
It's indefinite.
Indefined is it's hard for counting. So in 1 cube centimeter, okay, just the background aerosol loading is 10,000 particles, okay? This is the natural loading of aerosols. And if the loading is higher, like in a cigarette, the cigarette smoke, you see it. Okay, then it's 10 to the power 5. Okay, and then you see the dust, okay, because of the higher concentration. And during a day, an adult inhales around 1 billion aerosol nanoparticles. Okay? Keep this in mind when you read that you inhale some nanoplastic. I don't say it's not dangerous, but keep in mind that every day you breathe in and breathe out around 1 billion aerosol particles, and that's very, very normal. Okay? But in higher concentrations, they can affect health. Okay, so, and there we have to be careful, especially when, for example, working in the lab with aerosols. So, any questions to this? This definition you should know. Okay, so this you should know, you should be able to explain this, and you should know some of these points. Then I would like to go from health to another thing, and this is the so-called planetary boundaries. Do you, any one of you have seen this? Do you know what it is? Yeah, the name is there, Rockström. Mm-hmm. Mm-hmm. Okay, very good. So basically the idea is that our planet has a quite stable environment for over 10,000 years. And this is quite unusual, and we call it the Holocene. But since the Industrial Revolution, we are actively changed this situation, and this is called Anthropocene, okay? And the problem is that we bring the planet out of this stable environment. And we don't want this, because our development and our culture and everything is very related to these stable conditions. And then he said, okay, we need to maintain these stable conditions, and therefore he suggested boundaries in different fields, because it's not only about CO2, and it's not only about climate change, and you see that climate change is just one of the points we have to take care, but there are also others, and one is and when it's red, it's not good, and this is from 2009, and here you see from this year, so on Wikipedia you just find the original ones, not the original, sorry, the actual ones. And you see we're don't getting better, okay? And the thing is that he tried to figure out what is a threshold. So what is a measurable parameter for each of these boundaries? And once the threshold is overcome, we have a problem, because we cannot tell exactly what will happen, because these are not linear systems, okay? If you're over a point, there is a big risk that something happens or is connected to other points, and we really cannot foresee. And you also see how it's related to this class, why I'm showing you this. What do you think? Very good. Basically, the aerosol loading at all, right? So aerosol loading is one of the points, one of the planetary boundary, and you see that, no, it's not marked here, but the problem is that you see it here, but not here. We still don't have a fixed threshold. So we don't have a defined boundary for aerosol loading, because we have all kinds of different aerosols in the air. And they have different impacts. And it's really hard to find one measurement value to find which is a good threshold. So this is still part of discussion, but we know that it has effect on health, and since Industrial Revolution, the number of aerosols in the atmosphere is doubled now. And we also know it has an impact about the radiation balance of the planet, because more aerosols in the atmosphere will scatter the light back, right? This is also an idea to cool the planet. I don't know if this is a very good idea, but you find books who talk about a scenario to bring nanoparticles into the atmosphere and to cool the planet in this way. But it's not really good when we don't know what happens then. And it's also indirectly affecting the climate, because it's affecting cloud formations. So formation of clouds is very strongly related to a nuclei, and nanoparticles are nuclei of droplets. And for sure we know that in Asia the monsoon is affected. So time and area of the rainfalls is affected by the aerosol concentration. And this could be very nice, but in most cases it's not very nice, okay? And this is why aerosol loading is here so important for the planetary boundaries. So we have a topic here which is related to technology, but very, very easily related to the health of our climate or the stability of the environmental system. And here I took a slide from my professor in Bremen, and he has a quite nice overview. And here we see, okay, we talked about this one, environmental. We talked a little bit about health, not the details, but here you see, okay, smoking, medicine, asbestos, and all of this is related to aerosol technology. And you see also astrophysics, so Thomas Jüstel would love it. The formation of planets is related to coagulation. Eigenheim problem is called. So when the planets are growing, this is explained by aerosol physics. Energy has a lot to do with combustions also, right? Coal combustion, fuel injection in engines, diesel engines, and so on, where we have nanoparticles. And for us, as engineers, of course, we have here materials. Okay, materials is a extremely nice point. We have to talk carbon black. You see that, I mean, it's old numbers, 8 million tons per year. Titania pigments for, what is the one application of titania pigments? Sunscreen, right, or color. But sunscreen, very good. Zinc oxide also was an idea to put them in sunscreen. I'm not a big fan of this, but okay. Fumed silica, something you will find in our labs. And we will for sure touch these materials and how these materials are produced. Okay, and one simple example is what you see here. Why could this be interesting for the lecture? What do you think?
They have used, I think, black carbon for painting.
And how do they get the black carbon? You already... Yeah, very good, from charcoal. So the left one is the production method. Okay, so they use vegetable oil. And in the pyrolysis of the oil, when you burn it, you get what's called lamp black. Lamp black is this kind of black pigment, which is very famous in ancient Chinese calligraphy and also in the in the paintings. And you see also the production method is basically the same still today. So they burn something. What is happening to the burning afterwards? You see it in the image. What happens after the burning? It's not suction, but that's, you are on the right track. What is the guy doing basically? Yeah.
And like currently India, it will go to certain and it will be deposited there.
Exactly. So basically, he's in a tent.
Yeah.
Okay. And on the tent, you see that the particles are remaining while the air goes through. And then he's just scratching it. And when I was in the lab, I had a HEPA filter and I was scratching the nanoparticles I produced from the HEPA filter. So very similar. But there's a difference between him and me in the lab. Do you think he will live very long? Why? He inhales it, right? So he's not wearing a mask. And working with aerosols is not that critical, but you should wear a mask, okay? Especially when we talk about simple aerosols, SiO2, carbon black, and so on. That's not very toxic chemicals, but you should not inhale it. You should wear a mask, okay? The next one is this one. Do you know, it's again a Bible, so today is a lot of Bible stuff. Do you know what kind of Bible this is? It has a special name. It's a very famous Bible. Again, sorry? Gutenberg. Why it's called Gutenberg Bible? I don't know about the translation. It's a good point. I don't know. I have to check. But he printed it. And the Gutenberg Bible was one of the first major book which was printed by his way. He invented printing of books, right? And it was one of the first mass-produced books. And it's really famous for, I mean, of course, for the content, but for the artistic way how the book is designed. Okay, so a high aesthetic and artistic value. Until today, there are 49 books left in libraries. So if you have the chance to look at it, really look at them. They're extremely nice. And what's often forgotten is it's not only he had, for printing books, they had these metal plates of letters, and then they could rearrange it, right, and print the page and suck. Yeah, they don't have, like the monks, they have to write the book. But it's not only about the metal and the metal plate, because the old paintings were water glue based. So they took glue from the vegetables, or where they took the oil also, which they burned, and then they put some water in there, and this was the ink. But this doesn't work so well here, and water-based ink was also not so good because it doesn't stick so well to the metal frame. So he developed an oil-based ink, which nicely adheres to the metal plate, and he could print with a very high precision, but still using lamp black as the ink, okay? So keep this in mind when you look at these kind of books. And after printing books and using carbon black as a pigment, do you know what most carbon black is used for? So basically the industrialization of carbon black started here in the first half of the 20th century. And there's a very nice picture from Wikipedia, so you see how the workers look like which work there, okay? So it's not very healthy, okay? So this is all the pigments they get up, and probably the smoking helps because there's a filter in a cigarette, at least if he smokes with a cigarette filter. And how this was industrialized was there was natural gas, and then you just burn the natural gas, and from the burning, you see here the burning of the natural gas, and then you have these water-cooled channels, and below the water-cooled channel, you get soot, okay? And this is the carbon black, which can be scratched then. Basically, maybe I show it next week. If I have a candle and I have a glass plate and I put it in the candle, you will get the soot, right? It's nothing else than this. I will show it next week. And a lot of the soot also goes up, so you can imagine this was a really, really dirty environment there, as you see here. And these production plants, for example, in Texas, were very close to natural gas resources. So this was the early 20th century. Why we started to industrialize carbon black in the early 20th century? What kind of development or invention was done there and started mass production? Cars, exactly. How is carbon black related to cars? No, it's in one, that's tires, exactly. So carbon black is extremely important for tires. And with cars, we need tires. And most of the carbon black goes into tires. What is in Germany with natural gas? Do we have a lot of natural gas in Germany? No. What do we have here? Charcoal, right? So this process doesn't work in Germany. And there is a company in Germany, which all of you know. And basically I'm in a very good mood because the last week was very good for my football team, and Champions League was very good, League was very good. But this company, I mean, in the past the name was different. It was Degussa, not Evonik. Now it's Evonik. They had said, okay, we have the problem in Germany. We don't have much natural gas, but we have charcoal. So they changed the process as the one I showed you to this process. So now we have oil, and the oil is a distillate from charcoal. So now we talk about distillation, and then we have an oil. And we have a gas, hydrogen, which is a kind of a carrier gas, and then you saturate it with the vapor from the oil, from the charcoal, and then it goes again to a water-cooled channel, or this time here it's turning, so it's called the gas black process. And then half of the carbon black will go here, and it's a little bit small, but here are like knives, which will just cut this kind of cake growing here, and then it goes down here. And the other half will just go up, as we saw in the picture, but it will not be released to the environment, but they will put a filter here, and then they will reunite the two flows. And this is basically a second process, quite similar technically. What is the difference? Just as a repetition from the first to the second process. Yeah, the change of raw material, right? We have to adapt it to the situation. But at the end, we just need a source of carbon, and we have a source of carbon, and then we just adapt the process. And you see here 1 billion tons of furnace roofs. So this is from Evonik, so it's really a mass production. And the nice thing is these bags are extremely light, because all of this is carbon nanoparticles, and nanoparticles don't have much weight. So you have a bag full of particles, and if you have one bag full of sand, you can try to carry it. It's very, very heavy. And if you take a bag of carbon black, it weighs, I don't know, 1-2 kilos, that's it, even less, okay? So and this is because of the small size. Yeah, here is again, just to show, so tire production is mostly carbon black market from 22. I really like this Mortar Intelligence, but that's another thing. The others are really, really low percentage, okay? And then to come to your question, so if you have a tire, 30% of weight is carbon black. And that's a lot, because these bags don't weigh much, so a lot of carbon black, because the tire is heavy, and 30% by weight is carbon black. And this is how the particle looks like. There is no scale, but it's a few nanometers, so this is around 10, 20 nanometer in diameter. And what happens is, so you have rubber, and you have carbon black, that's it. Do you have any idea what the carbon black is doing to the rubber?
Is it filler?
It's a filler, yeah, but it has a certain... it's not just a filler to kind of fill the gaps, not only this. I mean, it also makes the tire black. That's, we wouldn't buy a red tire nowadays. We are so used to black tires. That's a problem. They try to replace SeO2, no, carbon black with SeO2, but then you have white tires and nobody, so they then make it black again because we are so used to it. But it's not only this.
Friction resistance?
Friction resistance, right? So by the amount of carbon black, you can play with the properties of the tire, friction resistance, and so on. There's this magical triangle in Formula One. I don't have it here on the slide, but right when it's always about the tires, right? When it rains or there's good weather, they always go in and change the tires. And this is related to friction and so on. But basically, so you have the polymer change and the carbon black keep the polymer change together, okay? So without carbon black, the wire would not have a quite long living time, okay? So the carbon black connects the polymer change. And then there is a third process, which is very important. So we had the two processes where we have a carbon source and then we burn it. And we have like a water channel where the carbon black is separated. And the third one, and this is a process we will talk very often in this lecture, is flame reactors. And here you see a patent of a flame reactor. And in the flame reactor, you have a carbon source. So in this case, it's hydrocarbon raw material. And you have a flow of oxygen. And then you have a flame. Basically, mostly it's a methane flame because you need high temperature. And then you have pyrolysis of your hydrocarbons. And then you have a second chamber, and this is here, is the reaction chamber. And in the reaction chamber, you generate carbon particles at a very high temperature. And do you know what happens in the third chamber? This is what happens here.
Medium flame burner?
No, it's not a burner. It's the difference. Cooling down, exactly. So it's water. You quench. You try to very fast decrease the temperature to quench. And this is a special reactor. Normally, the flame reactor can be just a pipe with one diameter, but here we have different diameters, and the idea of this reactor is to create a very broad size distribution. We will see this next week, the size distributions. But here they say, okay, if you use carbon black as an ink for the Gutenberg Bible or for whatever, you need a broad size distribution. Why? Because with a broad size distribution, you have very dense packing. Okay, you know this from cornflakes or whatever. And dense packing means very clear black. Okay? If you have a high porous structure, the black is not that intense. And they say, okay, what we need is we need a very low gas temperature. And here, even if we decrease the diameter, they ensure in the reactor a very low temperature that they don't have turbulent mixing. And if you don't have turbulent mixing, they have kind of low turbulence. And then you have a heterogeneous situation in your reactor, and it means at one point you grow a very big particle, and another one you get a very small particle, and at the end you get a broad size particle distribution, and this is the value of the product in this reactor. However, these flame reactors are extremely common in industry. So here you see carbon black, titania, zinc oxide, fumed silica. The numbers are quite old, so I have to update them, but you see the volume tons per year. And think about tons is really a lot for nanoparticles, okay? Tons is really, really a lot if you think about these bags which don't weigh anything. And you see most of them are predominantly made in these kind of flame processes. Why these flame processes are so good? Because they're extremely nice to scale. So the flame I worked in the lab has this size, and we easily can scale up it to industrial scale, to the big meter reactors. So perfect for scalability. No liquid byproducts. If you make nanoparticles with liquids, you have a lot of byproducts. You have better control about certain things, but you have to do something with the liquids afterwards, and mostly it's not water, right? And here you don't have any liquids. You just burn something, and then you need a little bit water to quench. You have high purity of products. That's really, really nice. So these flames don't give you really annoying byproducts in your, so you can get also highly crystalline products, and you can get metastable phases. Okay, we will learn about this because you create a particle at 2000 degrees and you directly quench it. So the crystallization you get is stable at 2000 degrees, but you will not, it doesn't have time to adapt to 20 degrees, okay? So you kind of freeze different phases, and it's just a few and fast unit operations, okay? You burn, you filter, that's it. Disadvantages is capital investment, so it's quite expensive to build these things. Safety, okay? Remind the guy from the carbon black plant. And there's also something about precursor availability. Okay, so because you need sometimes really complex precursors, and if you think about the example with natural gas and coal tar, right, precursor availability is not always given in the world. Okay, then we go directly here because I think we are nearly done. So I hope for today you get a little bit insight into the lecture. So I hope you learned what is an aerosol and you have an idea about different areas where we use this. Nothing about movement. I hope you learned something about carbon black, how we produce it, how we use it, and a small introduction into nanotechnology. So for the seminar, I will upload a paper this week, okay, in the folder literature. And I want you to go through the paper before you come. So you will have time here again to work on it. So you don't have to perfectly prepare the whole paper, but go fastly through it, okay? Because we will discuss the paper. You don't have to perfectly prepare it, but just read it quite fastly, okay? Then I will see you next week. And thanks again, or thanks a lot for the lecture. And yeah, if you have questions, just let me know, okay? So thank you.